Welcome to the next video on solving simple circuits. In this video, we are going to look at parallel circuits, circuits that are purely parallel. And so, just as before, we need to be aware of what the rules for current, voltage, also known as potential difference, and resistance are. So those rules are encapsulated in these equations. We have different rules for series versus parallel, so you need to be very confident in identifying the circuit that you're looking at, whether it is all series or all parallel, or there is also the possibility that it is a combination. And if it's combination, well, that's going to be the next video. That needs a little bit of its own treatment. So make sure that you know these equations and that you are comfortable with them. Okay, so we have a circuit here that we can see is a parallel circuit. Just as in our previous problem, they've given us an EMF, which was just once again the old and kind of old-fashioned way of saying what the voltage for the battery is, the electromotive force that drives the current through this circuit. So we know that our power source is applying 24 volts, but in this case, we have a lot of branches. So all of our currents, they have a choice of going through the first branch, or the current could go along and go through the second branch, or it could go through the third branch. So we could hit only one of these branches and still do a complete loop from the positive terminal to the negative terminal of our power source. So the rules for this one are going to be different. In a parallel circuit, the voltages and currents do behave differently. Now we're still going to set up a table like we did before. And so once again, that table was for calculating V, I, and R. And we want a line in that table, a row for each of the elements, each of the resistors, plus a line for the totals. So we go ahead and we fill in the givens that we have. We know that the total voltage here is 24 volts because that is the one applied by the power source. I have 3 resistors, and we can see that we have a 2 ohm resistor, a 3 ohm resistor, and a 12 ohm resistor. And the way that we're going to approach this still obeys the general rule, which is if I can fill in the last one in a column, we should be able to fill in the one in a column, and we can use the rules to try and fill in the rest of the column. And for any row, when I know 2 out of 3, I can use V equals I R. So look for anything where we can apply a rule and finish off a column or finish off a row. So in this case, I know all of the individual resistances, and I could calculate what the R total is. Now, when we're finding a total resistance in our parallel circuits, that rule was a little bit different, and it's not just in appearance. When we do this, when we do the math for this, if I take 1 over 2 ohms plus 1 over 3 ohms plus 1 over 12 ohms, I need to type in my calculator 1 over 2 plus 1 over 3 plus 1 over 12, and it's going to be a little bit unusual. If I go into my calculator and I type that, I'm going to get 1 over 2 plus 1 over 3 plus 1 over 12, and when I type that in, I got 0.917. However, this is not my resistance. This is 1 over my total resistance. So I need to take the reciprocal. I need to take the inverse. And you should have a key on your calculator. You could type 1 divided by the answer, but there's often also a key on the calculators that calls for taking it to the -1 power. Which is just a quick way of telling the calculator, hey, I want the reciprocal of this number. And if I calculate that, if I type that in, I get about 1.09. And that means the total resistance for this circuit is 1.09 ohms. I want you to notice an unusual feature here, and this is a big part of parallel circuits. This resistance, the total resistance for our circuit, is less than any of the individual branch resistances. So when we have a parallel circuit, when we add more resistors, when we add more branches, we actually get less resistance. And the reason for that is we're adding options, possibilities for more and more current to flow through. If I were to add one more branch, it's like opening another lane in the checkout line at the grocery store. No matter how high the resistance on this is, it's still another option, which means we can still move more people, more current through. So our total resistance will always be less than any of the individual resistors. Okay, well, if I have a low resistance, that does mean I'm probably going to have a pretty high current. And so if we take this number of 24 volts divided by 1.09, using V equals IR to solve for I, and when I solve that, I get a total current of about 22.0 amps. So 22.0 amps, and last time we copied the currents all the way up. As soon as I figured it out for one, it was the same for all of them. That's not the case for parallel, though. In parallel, it's the voltages that are all the same and the currents that add up. So what we're going to do is we are going to fill in our voltages. The first branch has a potential change of 24 volts. The second voltage is 24 volts. The last branch, or the 2 ohm branch, has a potential change of 24 volts. All of them are the same. And then we are going to calculate the currents and see if the currents add up to our total. 24 volts divided by 2 ohms is 12 amps. 24 volts divided by 3 ohms is 8 amps. 24 volts divided by 12 ohms, that's 2 amps. And when I go to add them up to see if they check, 12 plus 8 plus 2 gets me 22 amps. It checks out, we're good. Now let's actually answer the questions that were asked. This question calls for what is the reading on the voltmeter? That voltmeter is measuring our 12 ohm resistor. So I look in the line for 12 ohms. What is the potential difference? It is 24 volts. What is the reading in the ammeter? Well, all of the branches have separate amperages, so I want to pay attention and go, oh, well, my ammeter is on the line of the 2 ohm resistor. And so the current in this case will be 12 amps. The branch with the lowest resistance had the highest current. Okay. And finally, we have the question of the rate at which the circuit dissipates energy. A rate at which energy is dissipated is also known as power. Change in energy over time, joules per second, some number of joules per second. So the question is, what is the power of this circuit? We do it for the total, and in circuits, it turns out that the power, the rate at which the energy is dissipated, is equal to IV. So this was kind of added on. It feels like it was just an afterthought, and the reason for that is we can treat it like that. Once we figure out I and V, it is not very hard to take our 22 amps times our 24 volts and be able to calculate that this current uses up a 528. It is not hard to calculate that this circuit uses up 22 times 24, or 528 watts, 528 joules per second. So power calculations, once we get our V, I, and R down, it's just a quick follow-up to calculate. All right. So just like our series circuits, with practice and being methodical about it, we can answer these with a high degree of confidence. So make sure that you practice, make sure that you take care, that you're being careful about calculating your total resistance and double checking that. See you in the next video.